You know, the 8051 microcontroller. It's kind of like the unsung hero in the world of electronics. It's this tiny brain powering everything from old-school keyboards to heavy-duty industrial machines, a real workhorse. But have you ever stopped to wonder, how does this little chip actually talk to the world, and how does it keep time so perfectly? Well, that's exactly what we're going to dig into. Right, so how does a simple little machine like this control the world around it and keep what feels like perfect time? I mean, how does it sense what's going on, tell things what to do, and make it all happen with split-second timing? It really can seem like magic, but trust me, the answer is way more down to earth and honestly pretty clever.
And believe it or not, the answer starts right here. It's literally written on the chip itself, in its connection points. Take a look at this pinout diagram. You can think of it as a treasure map for electronics. Every single one of these pins is a gateway to the outside world, a potential connection to an LED, a button, a motor, you name it. This is how the 8051 physically shakes hands with reality.
Okay, so to really get a grip on that interaction, we need to talk about its I/O ports. I love this analogy. Think of them as the microcontroller's senses, its way of feeling and listening to what's going on, and its voice for shouting out commands.
So the 8051 comes equipped with 4 of these ports, named pretty simply, port 0, port 1, port 2, and port 3. Now each one is an 8-bit port, which just means it controls a group of 8 pins. So you do the math. 4 ports times 8 pins, that gives us 32 individual lines we can play with. And the best part? We can program each one to be either an input or an output. That is a ton of flexibility.
But here's a little twist. These ports aren't just for show. Most of them are serious multitaskers. For example, port 0 and port 2 can double up as an address and data bus, which is super important for talking to external memory. And port 3? It's got all sorts of special jobs, like handling serial communication. But here's the catch, and it's a big one. When a pin is doing its special job, you can't use it for regular I/O. It's a one or the other deal. That makes port 1 our true hero here. It's the dedicated I/O specialist, always ready for input and output, no questions asked.
All right, now this is where things get, well, a little tricky. There's a really important concept you have to get your head around when working with these ports. What you write isn't always what you read. The value you teleport to output on the inside might not be the same as the actual voltage level on the physical pin on the outside. Kinda weird, right?
So what's going on here? It all boils down to the difference between the latch and the pin. Think of the latch as the internal command. It's a little piece of memory inside the chip that holds the value you told it to hold. It's what the microcontroller intends to do. The pin, on the other hand, is the external result. It's the physical connection to your circuit, and its voltage can totally be influenced by whatever it's hooked up to.
And this is exactly why the 8051 is so smart. It has these special instructions called read, modify, write instructions. So let's say you want to flip just one pin on a port from off to on without messing with the other 7. How do you do that? Well, these instructions read the value from the internal latch, the intended state. They change just the one bit you care about and then write the whole thing back. This is absolutely crucial because it stops the chip from getting confused by whatever's happening on the outside.
Okay, let's look at a real-world example. It makes this so much clearer. In this circuit, we're telling the port to output a 1 to turn on a transistor. So inside the chip, the latch is holding a 1, no problem. But look at the physical pin. Because of how a transistor works, the voltage on that pin drops to about 0.7 volts. Now, if the microcontroller were to read its own pin, it would see 0.7 volts and think, hey, that's a 0. It would completely misread its own output. But by using a read-modify-write instruction, it reads the latch instead, sees the 1 it intended, and everything works perfectly.
All right, let's zoom in on port 0 for a minute because it's special. It's the odd one out of the group. The other ports can both push the voltage high and pull it low, but port 0 is what we call open drain. That means it's really good at pulling a connection down to ground to create a low signal. But to make a high signal, it can't actively push the voltage up. It basically just lets go of the line.
So if it just lets go, how do you ever get a high signal? Well, it needs a little help from the outside. You have to connect what are called external pull-up resistors. You can see them right here. Now, when port 0 lets go of the line, these resistors are there to gently pull the voltage level up to a high. Without them, that pin would just be floating in limbo, and that's no good for anyone. Let's look at some quick code to see this in action. First, we load the accumulator with the hex value 55.
In binary, that's 01010101, a nice alternating pattern, right? Then we start a loop. We send that pattern out to port 0, we call a delay to wait for a bit, and then we use the complement instruction to flip all the bits. 0101 becomes 1010. We send that out and just loop forever. The result? The pins on port 0 will be blinking on and off in this really cool alternating sequence.
Okay, that covers the microcontroller's voice, how it talks to the world. But what about its rhythm? How does the 8051 keep a steady beat, create perfect delays, or even count things happening outside? For that, we need to look at its incredible built-in timers and counters.
The 8051 actually has 2 of these little timekeepers, and you can set them up in one of 2 ways. First, you can use it as a timer. In this mode, it's basically counting the internal clock ticks of the microcontroller itself, like a metronome. This is perfect for creating precise delays. Or you can set it up as a counter. Now it ignores the internal clock and instead counts electrical pulses coming in from the outside world. Think about counting products on a conveyor belt. Every time one passes, it sends a pulse, and the counter just, well, it counts.
So how do we tell it what to do? The command center for all this timing magic is a special little place called the TMOD register. TMOD stands for timer mode. It's an 8-bit control panel where we can set all the options. By writing just the right byte to this register, we can configure timer 0 and timer 1 to do exactly what we want.
And if you look at the structure of KeyMod, it's actually pretty elegant. It's split right down the middle. The 4 bits on the right-hand side are for configuring timer 0, and the 4 bits on the left are for timer 1. It's a mirror image. For each timer, you have a bit to choose between counter or timer mode, and then you have 2 mode bits, M1 and M0, that let you pick one of 4 different ways for the timer to run.
So what are these 4 modes? Well, you've got mode 0, which is a pretty simple 13-bit timer. Then there's mode 2, which is really clever. It's an 8-bit timer that automatically reloads itself when it's done, which is awesome for creating continuous signals. Mode 3 is a bit of a special case, but the one we're going to focus on, and probably the most common one you'll use, is mode 1. It's a full 16-bit timer, and that gives you the biggest range and the most precision for creating all sorts of delays.
Okay, enough with the theory. Let's get our hands dirty and see how this works in practice. We're going to use our new friend, timer 0, and set it to mode 1 to generate a really precise digital wave.
And you'll find that the process for this is almost always the same, like a recipe. Step 1, you load the TMOD register to set the mode. Step 2, you load the timer's high and low bytes with your starting count. Step 3, you kick it off and start the timer. Step 4, you sit back and watch for a special overflow flag to go up, which is its way of saying, I'm done. And finally, you stop the timer, clear that flag, and you're all set to do it again.
So, here's our mission. We want to generate a 1.67 kilohertz square wave. That's just a fancy way of saying we need to create a delay that lasts exactly 300 microseconds. Now, since we're using a 16-bit timer in mode 1, it can count all the way up to 65,536. We want it to overflow after 300 counts, so we just need to start at 300 counts before the end. The math is simple. 65,536 minus 300 gives us 65,236, and in hexadecimal, that value is FED4.
And here's what that looks like in code. It's actually really straightforward. First line, we move the value 01 hex into TMOD. That sets up timer 0 for 16-bit mode, which is mode 1. Next, we load up our calculated starting value. Remember FED4? Well, the high byte, FE, goes into TH0, and the low byte, D4, goes into TL0. And the last step, we set the TR0 bit, which is like flipping the on switch. The timer starts counting. Up, actually, not down. It counts up until it overflows.
And what do we get for all that work? We get this, a perfect, precise, repeating square wave. By just putting this whole process in a loop, loading the timer, running it, flipping a pin when it overflows, and repeating, we've created a stable digital signal. And I can't overstate how important this is. This is the heartbeat behind everything from sending data to controlling the speed of a motor.
So, when you boil it all down, it's actually pretty poetic. The ports are the microcontroller's voice, and the timers provide the rhythm. And when you put them together, they can orchestrate just about any action you can imagine. If you really want to unlock what the 851 can do, mastering these two things is where it all starts.
So now you know the tools. You know how to give your electronics a voice, and you know how to give them a rhythm. The only question left is, what song are you going to make them sing?